All right, so there was the signal to go. So first of all, a wonderful good afternoon and welcome to this installment of the C++ fundamental tracks. We're going to talk about algorithms. So first of all, some people might not know me. My name is Klaus. What I do for a living is I'm a C++ trainer / consultant. Sounds pretty boring, sounds not particularly entertaining, but I try to help. For that reason, I've also written a book about C++ and do all kinds of stuff at conferences, and I've also running a user group. So as I said, today we're going to talk about algorithms. So let's quickly, just shortly, jump back in time where this all started for the standard library. So middle of the 90s, this paper was submitted for the standard library, the standard template library, written by Alexander Stepanov, in which he proposed a couple of things for the C++ standard. First of all, containers, basic data structures, vectors and lists and sets and maps, different ways how to store things in memory. However, these containers do not work on the data directly. That's the purpose of algorithms. They work on the data. And so, from a conceptual point of view, containers don't know algorithms and algorithms don't know containers, which is quite clever. However, now these have to know each other still, they still have to work together, and that's then the purpose of iterators. The abstraction layer in between that allows you to use any kind of container with many algorithms and the algorithms with the containers. So on this level already, this kind of feels like a toolbox. You can pick one thing, combine it with other things, and this pretty much is what the STL is supposed to be, a toolbox. Little things that you can put together in order to create bigger things. So this is kind of the feeling that I also want to give you now when we talk about algorithms, because in the end, it's a pretty hierarchical idea. So we'll entirely focus on algorithms. So let's talk about them. And let's have some fun with them, with algorithms and The Simpsons. Yay! Okay, we have to practice this. Next time you have to at least pretend to be happy. Okay, so we're going to deal with The Simpsons. For that purpose, and I introduced the cast for this talk. So there is, first of all, Lisa Simpson, the algorithm expert. Then on the other side, we'll have Bart, the algorithm ignorant skeptic. And of course, in between, we also have Maggie, the always interested C++ enthusiast. All right, I start by a little bit of code that we'll see use a couple of times. So there's a simple struct, a simple aggregate, aggregating two strings for the first and last name of a person and an integer. And then I'm going to use this person to create, well, The Simpsons. So I'm creating, in this context, 11 persons. Of course, the 5 Simpsons, Homer, Marge, Bart, Lisa, and Maggie. But then also 6 other Simpson-related characters like Hans Moleman, Ralph Wiggum, Milas van Houten, Ned Flanders, Jeff Albertson, and Montgomery Burns. So first column is the first name, second column is the last name, third column is, well, the age of the person. All right, and this is now what Bart wants to work with. So Bart has a first idea what to do. Then he find the youngest person in the vector of persons. So how is Bart going to do that? Well, first of all, of course, he checks if there is a person. So there's an if the begin is equal to end. If it is, then there's nothing to do. Okay, we're done. But else, well, then we might start with just taking a quick guess, and we guess that the first element, the begin of the table, is the youngest person, the smallest element here. Okay, and then we're going to iterate over all the other persons. So we start from the next element, so begin table +1, up to the end of the table, +++. And then inside the for loop, of course, we have to check if the current person is perhaps younger than the already identified youngest person. So we compare by age, the current person and the currently youngest person. But if the age of the current person is less than the youngest person, well, we have found a new youngest person, right? And so we remember this as the new youngest person. Well, and afterwards, in the end, we can just print the youngest person, whoever it is. Okay. Not bad, is it? Not bad. Sounds like it's right. But Maggie disapproves Bart's solution. Maggie doesn't like it. You know, Maggie is just 1 year old, but coincidentally, she is the youngest person. But Maggie feels this code is hard to read. It's an entire screen just to find the youngest person. Maggie finds that it's also hard to understand, even for a year-old. If she feels it's pretty verbose, easy to get wrong. She's feeling this might contain an error, and it's not really reusable. We would have to write this again and again whenever you find some youngest person. No. Maggie disapproves. Maggie, and there's of course this comment that is a clear indication that something is not perfect. Find the youngest person. The comment explains what this following code is doing. Not a good thing. Now, Maggie would use an algorithm. Maggie would go to CPP reference, of course. And she would go to the starting page and wouldn't look for something special. She would just look for this one link, Algorithms Library. She would click on that and come to a huge page. A long page with, now stay seated, don't fall off the chair, more than 200 algorithms. Ooh. But if you browse this long enough, you will come to a category of minimum-maximum operations. This is where she might find just what she needs. So what she needs is to find some minimum in a range. Oh, min element returns the smallest element in a range. That's it. So she clicks on that and comes to a pretty neat explanation. Okay, the first view is a little scary, I admit. Yeah, all the overloads that min element has. However, she now knows, in order to use an algorithm, she includes the algorithm header. And then, well, she might just try one of the first two overloads. It looks like two, it's actually just one. In C++17, we added cons expr. So all we have to pass is the range, the iterators to the vector of persons. Great. So she replaces Bart's code with a min element call. Begin table, end table, and this returns an iterator. Great. It doesn't compile. Doesn't compile for a very simple reason. How should min element know how to compare the elements? So if you now scroll down from this min element page, you actually come to the possible implementation. A really helpful point in order to learn how these algorithms work. It's not always given, but at least a simple algorithms always kind of give an example. But note, it's a possible implementation. It's not the implementation. Every library vendor, everyone who implements min element can decide on his own how to implement that. Yeah, this is just an example, but usually a good one. So min element takes two iterators, pretty much does the same thing that Bart has done. Oh, definitely an indication that Bart has done too much work. But here, at this point, you see that the elements themselves are compared by a less than. Less than. Doesn't really make sense on a person, right? Person A is less than person B. This does not sound reasonable. This sounds demeaning. So it just doesn't make sense on a person. Does this mean that we cannot use min element? No. There is another set of overloads. So there's a min element that accepts the range, but also a compare operation. That, if you provide it, allows you to specify how to compare persons. So instead of the less than comparison, comp would be called. And if comp returns true, comparing two persons here, then we find a new smallest element. So this is exactly what Maggie needs. So we pass compare, use comp here. And instead of just passing the two iterators, she passes a lambda 2. Two persons, by reference to const, they are compared by age and are returned true. So essentially what I've plugged in is the less than comparison on a person. Great, isn't it? This works. And it's better. It's shorter. It definitely is something that is preferable. So Maggie at least feels this is easier to read because it's shorter in the first place. It's probably also easier to understand. It's less verbose. It is shorter, for sure. And it's definitely easier to get right. Definitely. It's hardly possible to introduce a bug in this little piece of code. And this is probably more reusable. I can call min element in many places. I do not have to re-implement all this stuff. Good. So Maggie's happy, but we can improve on that. Lisa knows that. So Lisa would, because she's the algorithm expert, argue you can do even better with stood ranges min element. Ooh, stood ranges min element. Yes, that now is an addition of C++20, which indeed makes this even simpler. Again, on C++ reference, you find the stood ranges min element. Yeah, I know, which sound looks even scarier. I know. But if you just look on this line, you can either, first can include algorithm again, you can either pass to iterators. The second one can actually be different, could be a sentinel. You can pass a comparator again, and the new thing that I'm going to show, a projection. Or, and this is now what Lisa aims for, you could not just pass two iterators, but the range itself. So this thing, this is now what we call here. So we pass the table, stood less, but again, less on persons, this makes sense. So we now project the person onto its age value. So now less compares DH. Whoa, pretty cool. Short, readable, definitely better than before. But we can even do even better, because the default for the second is stood less, was precisely stood ranges less. And so we could even drop that, just use an empty set of braces. Whoa. Better, much shorter.
How does the shortcut work then? Because that seems to, if that's an algorithm you're supposed to put in, how does it work out that you actually need something less?
So the question was, how does this default actually work? Why can I just use braces? Well, because we know that the default will be a stood ranges less, so that's the default. Now this is what the compiler can figure out based on the definition of min element. Yeah. Great. So this is now so clear in itself that it's definitely time to drop the comment. We don't have to explain the code anymore. The code explains itself. It's self-documenting. Nice. And so Maggie is super happy. Yes. Bart is not so happy. Oh, sorry. Yeah, of course. The quote, what I've just shown is exactly what the industry, the C+ industry now says, and one of the proponents of that is Jean Parent. Many years ago, 11 by now, he talked in C+ seasoning about algorithms and said the following thing. If you want to improve code quality in your organization, I would say, take all your coding guidelines and replace them with one goal. No raw loops. This will make the biggest change in code quality within your organization. Oh, strong words, pretty strong words, but I actually agree. And so, I hope you do. Bart does not yet. Not convinced yet. Now let me put all the children to the beginning of the vector. Okay, now this is what Bart would do. You would first shortcut begin table and end table into first and last. Okay. Then you would run a while loop. Why? Well, because he's now traversing all the elements until he finds the first adult. This is when this loop would stop. So while there's a child, and while we have not reached the end, of course, move on. Okay. Then there's an if. If we have not reached the end just yet, and we have to do something, then in a loop, starting from the next element, of course, we would check if the element is a child, and we would pretty much exchange the two values. The element we are here with, at first, and the element from pause. And then we move forward by one in first. Works, right? Right? Is this correct? Okay. In this setting, I would also not raise my arm. Because, of course, you all believe, oh, this is a trap. This is a trap. If he's asking this suspiciously, there must be something wrong. But also, there's the feeling there is something not correct because you don't understand every single bit. That's the problem of this code. It is hard to read. It's hard to understand exactly the point. So, Maggie again disapproves the solution. She just doesn't understand this by just looking at it. And again, she just needs this comment to know what this is actually doing. Okay, so let's improve. Slowly, step by step. These couple of lines. Yeah, that's a common pattern. This pattern is the pattern of an algorithm. This is an either swap. So, but these three lines can just be replaced by an algorithm. So please swap the two elements at these iterator positions. Okay, makes this short already. Let's take a look at this line. What is that? Of course, it's another algorithm. This is a find if not. And if you read this, oh, okay, it's clearer. Find if not is child. That makes a lot of sense. Is child, please assume this is a function that I pass. If it's a function, then we would pass a function pointer at this point, which might not be perfect from a performance point of view. Function pointers are always a hindrance to the compiler. Function pointers cannot be as easily inlined, so we should prefer to pass it as a function object. So we might just wrap this in a simple lambda that calls the function. And this is actually easier to inline. Now see core guideline T40 for a couple more examples. Okay. Still there is this comment. Definitely an indication that we can do more. So this looks like a partition, doesn't it? Yeah, I think Lisa is correct. This entire thing, this entire algorithm actually is a partition. Absolutely. So, stirred partition. What is a stirred partition? Well, it's one of these algorithms that you definitely should know. So, given a set of any values, some of them are in one group, some of them are not in the group. So, say we're looking for all the yellow elements. Now, with a partition, you can just put all these yellow elements to the front. Now, in our example, this would be the children. So a partition separates two groups of elements. Now, here the yellow and the blue. All right, that's nice. Again, the code is so much shorter, so much cleaner. And again, the name of the function already suggests what this is doing. I don't need a comment for that. Good. But you now also got this idea again. Partition is nothing but a combination of other algorithms. There might be neater swap in there might be a find if not. It's just little pieces that are put together for a bigger context. That's exactly the idea of the STL and also of these algorithms in them on their own. All right. But probably we can still do better. Absolutely. So again, we might be able to just use the C++20 ranges form of a partition. So, stirred ranges partition. And as you can guess, yes, we just have to pass the table. We don't need the end, begin and end anymore, which is so much more convenient. Even shorter, again. All right. Now Maggie is happy, because this is super easy to read. It's almost impossible to beat in terms of simplicity. It's easier to understand also, just because of the name. Partition communicates. Way less verbose and so much easier to get right. And if you look at this piece of code, what would you do wrong here? I mean, I don't say it's impossible. Yeah, still you can mess it up. But this is so short, so little, so few pieces of code that there's really almost no possibility, no opportunity to introduce a bug. This is great. This is amazing. Okay, and of course it's reusable. Partition itself is reusable. I can call it in any other context. So now, for instance, what if you're looking for not the children, but say the elderly persons, the senior citizens? Well, all I have to do is just to do one little change. Is senior citizen. Now, the elderly person I put to the front, and the second group is the other people. Very small change in one little place of the code, and it's simple because it's readable, because you know what is going on. You do not have to go through a lot of code to find this one place that you might have to change, but is there something else? No, this is simpler. So perfect reuse, because the algorithms have a name, can be called again. All right, now part counters. What if I wanted to keep the previous order of the senior citizens? Well, but Elisa, of course, the expert, knows that Bart doesn't have to reinvent the wheel. No. Don't reinvent, look around. This is a perfect opportunity for a stable partition. So, if you take a look at CP reference again, you'll find that partition is not just some algorithm, there's an entire category of algorithms. Partition operations. So there's the classic partition, of course then the range is partition too, but there's also a stable partition form. The stable prefix now tells you that the previous order of something, in this case the first and the second group, is preserved. And if you take a closer look at all the algorithms, you'll find that there are other stable algorithms, stable sort. That's nice. Because here, by not just knowing what this little prefix means, you can immediately guess what the other algorithm is doing, what properties it has. This is great. And so this is pretty much what all these algorithms do. Little prefixes. Is, okay, that's a question, is partitioned. Copy, okay, that's an algorithm that preserves the original range, copies into a new range. So, does not modify the original, but copies elsewhere. Very consistent naming convention. Pretty consistent indeed. Not perfect though. Yeah, don't claim that. Cool. However, we might have other ideas also. So Bart says, what if I now wanted to put the senior citizens last without changing their order? Now, of course, you could just change the stable partition again, but we could do something else too. Now that we have this stable partition, we could just do a rotate. Yeah, well, that could be a rotate. Stable partition returns an iterator, a position, which we can use to rotate this entire range to, put the senior citizens to the end. All right, not bad. Very simple, very quick, and now as we see the name again. Wow, that's simple and fast. But what would happen if I pass pos last? Ooh. That would be UB, undefined behavior. Yeah, unfortunately, the rotate algorithm actually requires that you pass first the beginning of the range, third the end of the range, and then in between the position of the element that you would like to be the new first element. But this element in between must be in the range between begin and end. If it is not, undefined behavior. Why is that? Why doesn't the algorithm just check that it is? Well, either because it's very expensive, so we might be able to do this, but we do not want to check this for instance, in a list. That would be very, very expensive indeed, or it might just not be possible. So rotate just cannot do anything. That's on you. You have to make sure that pos is a valid, the middle element in the end is a valid position somewhere between this and that iterator. However, Lisa has a nice way around that. Why not just use the ranges rotate? I would pass the table and pass. And again, how would we misuse that? Very unlikely, very, very hard to misuse. Not bad again. All right. But let's do something else. Third problem. Now Bart needs to sum up the age of all persons. All right. So he suggests to introduce an integer, total age. Initializes this probably to 0. Then to write a for loop over all the persons in the table. And then to, of course, add the age of every person to the total age. Afterwards, we could print the total age, for instance. Well, not entirely bad. It's short, it's clear, and of course that's the point. We want to have code that is easy to read, easy to understand. But still, there is an algorithm for just this purpose. We could use accumulate. So, std accumulate. A classic from the very beginning of C++, but a slightly more complex algorithm. First of all, you would have to introduce the numerics header. That's special. So there are few algorithms that are not in algorithms, the numeric algorithms. Okay. So then accumulate itself takes a range, but then also an initial value, an init value. So if you sum things up, where do you want to start? Okay, probably 0 in most cases. But accumulate can do more too. Accumulate also is an overload that addition allows you to express a binary operation, the fourth parameter, which we now need for our adding the total age. So, why is that? Well, the class accumulate, the one that only takes init, runs a for loop over all the elements and just adds them up. But again, that's the point. Adding a person, adding int plus person, doesn't make sense. This is not really what a person should be able to do. So that's exactly where the second form comes in, where again you can specify how the addition should work by means of a binary operation. That binary operation, this op, takes this initial value, takes one of your elements, and, well, sums them up. Good. So, instead of calling this function, we could call accumulate. By first passing begin and end, then by passing an initial value, so 0 in our case, and some lambda that knows how to add a person to an age. Consider this some kind of addition operation. It really is. So left-hand side operand, right-hand side operand, and it returns the new value, which is then again given internally to the accumulator, the initial value, and summed up. All right. And we would print the age again. But now, why is this exactly better? Wasn't the for loop simpler? Wasn't the for loop just more readable? Well, perhaps. However, as Lisa knows, there is an advantage. Look at the const. Yeah, this avoids the ITM anti-pattern. ITM. C++ loves abbreviations, so this is no exception. ITM stands for initialize then modify, which Conor Hoekstra talked about a couple of years ago. And he plainly said in the title, my least favorite anti-pattern. Initialize then modify. First, creating a value, then changing it, and then using it. That's not what we like to do anymore. So we really strive for making things as constant as possible. So prefer to keep things immutable. This helps. And you kind of got the idea also today in a keynote presentation. It is pretty much about this immutability. So perhaps this is an argument in favor of accumulate. Okay. But what about performance? Of course, performance. C++ is all about performance. And now I've hidden the loop. Essentially, this is what accumulate is, behind a function. This must make a difference. This must slow my program down, correct? Well, no, it's not slower. Let me show you. So, let's take a look at this raw for loop. And so, here in this Compile Explorer example, I have a sum function that sums up doubles in a vector. Okay, pretty simple function. This version here does it by means of a for loop. And so using Clang 16, screenshot from a couple of versions before, and using all three, of course, this gives us 13 lines of assembly code. Okay, now I'm going to switch to the accumulate version. What you now have to do, and it's simple, it's really simple, all you have to do is to look on the right side. Yeah? Do not look away, do not blink, and okay, where's the difference? Now that I use accumulate, where's the difference? Oh, you have not seen it. I go back. So again, do not blink, and I go forward again, and where's the difference?
Syntax highlighting.
The syntax highlighting, correct answer. And that's it. There is no difference from a code perspective. There is not. It's the same, exactly the same assembly code. So apparently this function template is not a hindrance for the compiler to do the optimization. It's just as fast, it's just as good, but potentially more readable. Wow, they are fast and elegant. I'm deeply impressed. I'm still wondering why accumulate is so complex. Okay, and I think this is where Bart does have a point, absolutely. So complex is, well, not the simplest of algorithms around. Not the most intuitive, perhaps also. However, even for that, there is some kind of reason. And this is what Ben Dean has talked about in 2016. He's talked about accumulate for 60 minutes. So he has given an entire talk about std accumulate. And he demonstrated quite impressively that he can use accumulate for pretty much everything. So he claimed at the time that you can use accumulate to implement almost every other algorithm. I think 2 did not work, but every other algorithm. So yes, you can use accumulate to find elements, if you insist. You can even use accumulate to sort. I would not do that, but it works because of the way accumulate is implemented. You define the initial value, you define the operation, you can pretty much do anything with it. So it is the most generic algorithm that the SDL has to provide, has to offer. Okay, cool. Of course, and it's perfectly reusable again. Let's use this on a vector of floating point values. But please, take care of the initial value. Okay, again, this may be something that counts as a little trap, perhaps. If we now have a vector of doubles, and if you call accumulate, but then use the 0 at this point, whoa, then we might be in trouble. Accumulate deduces the type of the value that it passes here. So it deduces this as a t, and uses this t also as a return value. And perhaps you remember how it works internally. So this initial value is updated again and again and again, and in the end just returned. Which means, yes, we are now truncating every single double. We definitely cannot expect the correct result. So, almost for sure, we have to use the right value, of course. Oh, there's a slide for that. So the t is deduced and used as a return type in all versions of accumulate. Okay, so of course we have to use 0.0, or just .0 if you're a little lazy, or 0 dot, but it should be a double value, of course. But now you realize this is a little bit of a trap. And there are people in some companies, not in yours, of course not, but there are some people that still do copy and paste. And if they copy some accumulate call with such a number, they might forget to adapt the type of this initial value. It happens. It's easy to happen. So perhaps, as Lisa also suggests, perhaps it's not a bad idea to make it explicit. We want a default double. And this might actually help. This might actually protect against those that still do copy and paste, because probably double is more visible and they might now see, oh, double, I need something else. This might be a good solution for that. Okay, and if you missed the 0, you can of course put this in the braces still, yeah? All right, so.
Will that cause parallel warnings?
Oh, this would be great. I actually tried this a couple of times. No, there are no compiler warnings. And so this was the question. Are there compiler warnings if I do that? No. This is these unfortunate implicit conversions of built-in types that we wish we could control better. Now, you would have to use an explicit compilation flag, which is not part of W-all and W-extra. So it's not something that we easily get. So, what is another question, another idea? What if I wanted to speed this up with many threads? Okay, good idea, but unfortunately accumulate does not help you here. No, unfortunately not. This is where you have to switch to another algorithm. This is where we might use a C+17 reduce instead. Accumulate is an algorithm that promises to always accumulate from left to right. This is a strict thing, so left to right. But this gives you an advantage, of course. If you do have double values, you could sort them from small to big, and then your sum might be a little more accurate. Reduce, okay, reduce does not give you this promise anymore. Reduce is the algorithm that, however, you can optimize, that you can parallelize. So first of all, again, this is a numeric algorithm. And there is pretty much the same version that we also used for our accumulate. So reduce takes 2 iterators and initial value. Same idea. T is deduced and returned. There's also a version that allows you to omit the initial value, however. That's something that accumulate does not do, but reduce does. Okay, this might be a slight advantage. But then, most importantly, at least for the optimization, is the middle overload. This reduce takes an execution policy as a forwarding reference. That's one of these scary parts again. Ignore that. An execution policy now gives you the ability to tell the system how to parallelize that thing. If you scroll to the top of this algorithms page, you'll not find something about execution policies. And there's actually a lot to use. Okay, a lot. There are 4 options that you have. So in C+17, you can use seek. Seek means, please run it sequential. Pretty much nothing changes to the original thing. If you use par, however, then threads would be used. Now, if you're asking how many, okay, I cannot tell you. That pretty much is something that is up to the system. You can just say, please do, but it cannot really you choose any specifics. There are no knobs to turn. It's a given. You can also call par unseek. Unseek is specifying that you also would like to use SIMD operations. So not just thread parallelization, but instruction parallelism, if possible. Probably for reduce, this might make sense. And then the one option that was kind of missing was added in C+20, just unseek. Yeah, no threads, but please do SIMD operations. So we could just call this reduce by first passing std execution par, then begin and end, and perhaps the initial value double. Okay, now note, this now runs in parallel. So you might slightly change the result of your accumulation. Reduce always promise to do this from left to right. Reduce does not. That's the point why it is able to do this in parallel. But if you have first properly sorted your doubles, now of course the result is different. Just keep this in mind. It's not a huge problem, but if you need a specific result, if you have ordered it before, reduce might not be your friend. That's great. And so simple. And indeed, I believe this is really simple. The simplest way to parallelize such an accumulation. And you could drop even drop the initial here, the initial value. Sure, I showed this before. You can just remove that. And then this problem's gone also. Wow, this is so cool. I love this. Perhaps you now have an idea why Jean Perrin said that. So, no raw loops. This will make the biggest change in code quality within your organization. Of course, you might have exaggerated a little bit, but I think the point is true. It is simple, it is readable, it is elegant, it has all those qualities that we usually look for. So, okay, I completely agree now. But does this mean that I should not use for or while loops anymore? Am I now forbidden to use them? No raw loops? Okay, no. This is not what Jean Perrin is saying. In his talk in this C+ seasoning, he actually explains this quite well. So, for instance, Bart asks, if I would now have this vector of persons, if I want to print them, do I really have to use an algorithm like copy in combination with an O-stream iterator of persons? Whoa. Or would I have to use a for each that takes a lambda that writes a C out, which is probably a little more digestible? Do I really have to do that? Isn't this overly complex? Isn't this less readable? Well, it definitely helps to know your algorithms, but it is not forbidden to use for loops. So now, what is a raw loop by definition from the C+ seasoning talk? Well, Jean has an entire slide on that, and tries to make a point. If you're writing a range-based for loop, and that is the good loops, this is the loops that are usually simple, and if this range-based for loop contains perhaps one function call, or perhaps a simple combination of function calls, so if the body is short, precise, simple, then please use that. The entire point is to make the code readable, simple, digestible for other readers, and if this is the best thing you get, please use it. But if things are more complex, well, then probably it is time for an algorithm. And so, when is it time? What is a rule of thumb? Well, perhaps indeed up to two things that you do. Or, as Tony van Oort has put it, 9 times out of 10, a for loop should either be the only code in a function, or the only code in the loop should be a function, or both. That might be a good rule of thumb indeed. So it's about simplicity. Keep the things simple. Whoa, by now I just love these algorithms. But there's so many, more than 200 in C+20. How can I learn more about them? Well, there are a couple of great talks to watch. For instance, Lisa would suggest C+ seasoning indeed. But it is just the first half hour. So just that you know, in the first half hour, algorithms are discussed. And this is the talk that made a big impression on the audience. I believe this is why this talk is referred so much. But there's another great talk, especially if you want to get this overview. 105 STL algorithms in less than an hour. Okay, I know. If you've not seen the talk just yet, what you're thinking is not what this really is. No. This guy is not doing, in a 60-minute talk, 105 STL algorithms in detail, 40 seconds per algorithm. That would be crazy. No. What he's doing is really to give you this overview. What is available? Which algorithms belong together? Where's the group? How are they connected? Which are usually used in combination? That's what he teaches. And so this is probably a great follow-up talk if you want the overview. But if you want to see them in action, then perhaps this is the talk you're looking for. Algorithm intuition. In this talk, Conor Hoekstra, and actually it's the first of 2 parts, so there are 2. In this talk, he is not just explaining simple algorithms, he's using them for practical problems. So there's a problem, how do we solve this elegantly? It comes up with a couple of really elegant solutions using algorithms. Solutions that, if you see them, really sound like an amazing idea. So also a very good talk to get an impression why these algorithms are so valuable. So, don't be like Bart and write all your for while loops manually. Prefer to use algorithms. Ouch, this hurts a little. But I see you're right. Algorithms are simple, elegant, fast, and removes so much potential for errors. Prefer to use the C+20 ranges algorithms. They're even simpler, and a couple of these usual problems disappear. And remember the conventions and a few pitfalls. So for instance, accumulate is one of these examples, but also the algorithms that take 3 iterators. Usually they expect the special thing in the middle. Don't forget that. And learn more about algorithms. There's always more to learn. How do they work? Which algorithms are available? How do I combine them more efficiently? That's a great fun thing. All right, so that's the takeaways, which means that I'm willing to take a couple of questions. Thank you.